So I know we've talked about vectors, but now we're really going to get into vectors and exactly how you draw them and how you add them. Okay, so let's just get going. So vectors, again, if you're drawing a vector, it's just an arrow in the direction that you're going. Okay, but if it's at an angle, right, if it's not just north, south, east, west, then it gets a little bit more difficult. So if it is at an angle to the east or north or south or west, we can use all these different coordinate systems to tell us about our angles, right, and about our directions. So we can use the rectangular coordinate system, and so that's basically measured counterclockwise from the x-axis. So you start at the x-axis and you go counterclockwise. So this is pretty much how you measure all your angles in math. So this is, the method that math uses. Then we can use the bearing coordinate system, and that's clockwise from the y-axis. So this is what is used a lot in navigation, and when you're basically looking at a compass and it points due north, and then you take an angle from north, but this time we're going clockwise. So this is when it's used a lot in navigation. And then there's navigational coordinates, where I say it's north, east, south, west, or I say how many degrees it is away from the north or away from the east or something like that, okay? So for example, here's an angle, right? That can be written in a bunch of different ways. So we have, of course, our north, south, east, and west. And so I want to know what are all the different ways that I can measure this, okay? So again, first was a rectangular coordinate system, which is counterclockwise from the x-axis. So here's my x-axis, right? And counterclockwise is this way. Okay, so as it says, it's just 25 degrees. That's our rotational coordinate system. It's 25 degrees away from the x-axis going counterclockwise. Then we had what did we have? We have our bearing coordinate system. So that's measured clockwise from the y-axis. So here's my y-axis right here. So that would actually be starting at the y-axis and going clockwise, which is opposite direction. So that's going that way. So I need to know what angle that is, and that would be my bearing. Okay. So we know if this angle down here is 25, then this guy right here needs to be 65 degrees. How do we know that? Well, we know this is a right angle. So therefore we just go 90 minus 25 and we have 65 degrees. So that is my bearing. So when we're looking at the bearing system, we have a 65 degree angle, okay, which is again clockwise from north. Then we have our navigational ones, and these are going to be your most common. Okay, so what do we have? We have this arrow is going in the northeast direction, but I need specifically how is it going from northeast. So if you start east here in the x direction and you go 25 degrees north of that, north is going, to the top of the page here, then I have that 25 degree angle. So how do we say that? We say that that's 25 degrees north of east. Another word that you can replace of with is north from east. So that means you start at the east and then you go north of that, okay? So that's, we can say 25 degrees north of east, meaning start at the east and go 25 degrees north of that, okay? But there's always a complementary angle to writing an angle in that bearing system, and that would be east of north. So how do we do that? Well, if we wanted east of north, we start north and we go east of that, but of course in a kind of a circular motion, and that is therefore 65 degrees east of north. Okay, so that means you're starting north and going east of that. So those two things are complementary. If you gave me either answer there, 25 degrees north of east, 65 degrees east of north, those are perfectly acceptable. Either of those, I would accept either of those as answers, okay? That's going to be our most common thing that we use in Physics 20 though, okay? So this is basically what we're always going to be using. You still need to know rectangular coordinate system and the bearing. And if it says that, you need to know what that means, but this is what we're going to be mostly using. Okay? Another way of writing this 25 degrees north of east would be like this. You go east, start east and go 25 degrees north. Okay? And same way, another way of writing 65 degrees east of north is north 65 degrees east, meaning start north and then go 65 degrees east of that. Okay, so that's all the different ways that we can write this one angle, which is a lot, but again, we're going to use the north of east, east of north most often. Okay, so let's try that on another one. So we have an angle all the way over there. So in all our different systems, I want to know, how do we write this angle? Okay, so we had a rectangular coordinate system which started here at the x-axis and went counterclockwise, so it goes all the way around like that. Okay, so if I want to know my rectangular coordinate system, well, I know this half is 180 degrees, right? From the x-axis back down to the x-axis here. And then we have an extra 40 degrees. So I need to add those two together to do my rectangular coordinate system. So that is 220 degrees in my rectangular coordinate system. Okay, so there's that. What did we have next? The bearing. Remember, so bearing starts at the y-axis and goes clockwise, not counterclockwise. So that one starts here and goes clockwise. So I want to know, what is that angle? Okay, so again, I know from the y-axis to the y-axis is 180 degrees. So I just need to figure out what this guy is. Okay, what is that? Well, again, we know this is a 90-degree angle. So 90 minus 40 is 50 degrees. Okay, and 180 plus 50 is going to give us 230. So my bearing is 230 degrees. Okay, and then finally we want our the ones that we use most, which is our navigational coordinate system stuff. Okay, and so in that case, we just want north of east, east of north, all that fun stuff. So again, we know we got north, south, east, west. So this guy is going in the southwest direction, right? But of course, we need to say exactly how much. So if we look at the 40-degree angle, that's starting west and then going south of that. So we could say that it is 40 degrees south of west, meaning south from the west. Or, of course, if you start south and go west of that, that's 50 degrees. So you could also say it's 50 degrees west of south. Okay? And then, of course, the other ways you can write that is like this. Again, I will never be using this. It's just if a book says it or a question says it, it's just so you know what that looks like. Okay? So that's how we write angles. Which is really, really helpful, because then when we have vectors that aren't just going north, south, east, west, we can figure out how exactly to communicate where they are traveling. So we have a few ways of adding vectors. So we can use graphical, meaning use a scale diagram and measure. So if it says, something goes 3 meters north, then measure, a 3 centimeter line and have it pointing north. And it says then they went 2 meters to the east, so then measure out a 2 centimeter line going east, and then you can figure out what this is, what the hypotenuse is, using Pythagoras, or you can just do it, and you don't even need to use Pythagoras at this point, if we're doing graphical, then you just measure it, like physically measure it with a ruler, and it will actually line up. And then physically measure the angle with a protractor, and it will line up. Okay, so that is using a scale diagram. Obviously, I didn't want to draw 3 meters, so I drew 3 centimeters. Didn't want to draw 2 meters, so I drew 2 centimeters. And so therefore, this should be the same, or the correct answer, but in change centimeters to meters, and that angle will be correct. So that's one way we can do vector addition. The one that we'll be doing, of course, more often is the analytical, where we're going to break vectors into x and y components, and then we'll add them algebraically. How much is something going north? How much is something going east? Stuff like that, okay? A note. When you are adding vectors and you're drawing a vector diagram, you need to draw tip to tail. What the heck does that mean? The tip is the arrowhead, and the tail is the end of the arrow, okay? So, for example, something goes north and then northeast. You draw the north vector, and then here, at that point where you drew the arrowhead of the north vector, it's got to go the northeast. Sorry, I know I'm bad for having my phone on. All right, so there we go. And then, of course, my resultant vector is this F3 one right here. So then you draw the resultant vector. So I want to know, like, what direction did they go in? Then what was their total displacement? Then I need to figure out, okay, well then from the beginning of the first one to the end of the last one, I need to draw the resultant arrow. Then I can figure out the measure of that. I can figure out the angle, and that will get me the resultant displacement, okay? Anytime you're doing this, though, you have to choose a direction to be positive because, again, now we're looking at northwest, east, south, so it's going to be kind of difficult. So make sure you choose either north or south to be positive, and then east or west to be positive. Doesn't matter which one, and often in different cases you'll have to do both. You'll have to do a north-south direction to be positive and east-west direction to be positive, okay? All right, so here's a few different types. We're just gonna go with one-dimensional and two-dimensional here, and then I'll do a whole other video with the three-dimensional, because that is they're definitely big questions, so I'll just do a whole new video with that, okay? So I want to add a 4-meter south vector and a 3-meter north vector, okay? So if I want to draw this using actual vector addition and diagrams, then what am I going to do? Okay, well, we're going 4 meters south, so I'm going to call that the first one, D1, okay? So that's what's happening. So if we go south, we draw an arrow going south. Okay, there we go. That is my first vector that I'm calling D1. And then we're going 3 meters north. So again, I want to draw a vector, i.e. an arrow going north. But of course, since this one's 4, this one's 3, it should be smaller. Okay, about approximately 3/4 of the length. Again, you don't have to be perfect, but as long as it's approximate, okay? So there's my second displacement vector. So what's my resultant displacement? It's this right here, right? It's ending up further south than it did north, okay? So let's go ahead. A lot of the time we're used to defining north as positive, so let's just go ahead and do that, okay? And I will know my total displacement will be just the resultant addition of these two vectors as long as I keep direction into account. Okay, so my first vector was 4 meters south, so that is negative 4 meters. And my second vector was 3 meters north, so that's positive 3 meters. Okay, so guess what my resultant displacement is? It's, of course, negative 1 meters. And I know that since I made north positive, makes total sense that it would end up south, right? That's what we found, is that here's where it's ending, and that is, of course, still a meter south of where it started, and that's what displacement is, okay? So that's how you draw a vector diagram when you just have one dimension. So that one, again, we probably don't need it. It's really not that complicated, so let's get on to 2 dimensions, because that's when we really start needing vector diagrams. Okay, so we're going to add 2 right angles, 2 dimensions at right angles. Right angles are really nice. And then we're going to get into non-right angles. Okay, so let's do this. We have 3 meters north. So I'm going to go in 3 meters north. So I'm going to draw a vector 3 meters per second north. So here we go. We're actually talking about velocity in this case. I'm going to call that V1. And then 4 meters per second west. Okay, so I'll do that in a different color here. So 4 meters per second west. I'm going to try to draw as straight of a line. And of course, it should be a longer line than my 3 meters one. Okay, so we'll call that V2. So to draw my resultant vector, I need to go from the tail of this guy to the tip of this guy. Okay, so again, the starting point to the ending point. And this is my resultant vector. Okay, so if I want to add these two vectors together, and I want the resultant vector, the resultant velocity, well, again, directional stuff matters so much, okay? And because it's directional, not only do I need to find the direction, I also need to find the angle there. Or do I need to find the actual velocity? I need to find the angle as well. Okay, just to make this easy, let's make north positive and west positive, because of course those are the only directions we're going in those respective one-dimensional directions. Okay, so of course I need to use Pythagoras here, so that's what I'm going to do. And here we go. So the 3 meters per second, I'm going to square that. I'm going to take the 4 meters per second and I'm going to square that. Now, once we're inside the doing of, what am I trying to say? Once we're actually doing Pythagoras, the positives and negatives don't matter much, okay? But now here everything is positive anyways. So I get 5 meters per second. Look at that. So that is the resultant velocity, or at least the speed, but it's not actually the velocity because I don't have a direction yet. So I need to find that now. Okay, so of course I have my opposite and adjacent sides, so I'm going to use tan. Okay, so that's going to be V2 over V1, and that's going to get me the angle. Okay, so of course my angle is going to be the inverse tan of V2 over V1, which is 4 meters per second over 3 meters per second. Okay, and that angle is 53 degrees. Okay, and I should have put 2 significant digits here because I don't want to bring that down to 1 significant digit. That's silly. And then we'll say that that is what? Okay, well, we started north and then we went west from there, right? Always know where it's ending. So it's actually going west from the north. So this is west of north. You'll get better at that as you do more and more examples, because at first you're like, wait, what does that mean again? Okay, so there's actually 2 parts to that question. Always remember that when we're figuring out resultant vectors, we always need direction. And now that our direction isn't just north, south, east, west, we don't need a negative anymore. We need an actual angle with those directional coordinates. Okay, so just go practice a few of those, and then we're going to go on to adding together non-right vectors after this.